One thing I find hard to understand are these concepts of simplicity, beauty, and naturalness that you mention in the book. I never heard of these terms in applied physics, material science, and engineering. So what does it mean that physicists rely on beauty, at least the physicists that work on particle physics and theoretical physics?
What I'm explaining in the book is that in the foundations of physics, people have come to use very specific notions of beauty. And those are not exactly your everyday ideas of beauty, where you would say, well, a sunset is beautiful, or those flowers are beautiful, or that kind of thing. It's a very rigorous type of mathematical beauty. And they're just applying this to the new theories that they develop. So the new theories have to be beautiful in a very specific kind of way. The brief summary of the book is that I'm saying where you're putting the carriage before the horse, right? Yeah. You should not start with assuming a specific notion of beauty. You should try to find out what nature is telling you, and then you will find beauty. And it may not be the beauty that you expected, but we will come to find it beautiful just because that is what has happened historically. So these ideas of beauty that physicists are using in the foundations of physics now, one is simplicity in an absolute sense. So I don't mean Occam's razor, which is really a comparative judgment, when you say, okay, so I have two theories and they both describe the same data to the same accuracy. I take the simpler one. So that's a good scientific criterion. I mean that in the foundations of physics, scientists are urgently trying to find theories that are simple in an absolute way. And one area where this is particularly obvious is this quest for a unification of the forces, or even a theory of everything. So that they just have this assumption that as we look deeper into the structure of matter, it has to become simpler. And I'm like, well, why? Why does it have to be the case? Why can't it be that maybe it gets more complicated again? We actually don't know why you're making this assumption. It's not justified. And so philosophers would call it a metaphysical commitment. You just make this assumption, but it's not based on evidence.
Is it inductive reasoning?
Well, no, it isn't. That's exactly the case. Yeah. It has not. That's exactly the point. It's like historically, it's not been the case. You could have said, well, take who was it? Aristotle. I keep mixing up the Greeks with this theory of the four elements.
You have it in your book, right?
Yes, in the book, right. I've drawn this great diagram myself with the four corners, and so that was a simple theory. And you could say, well, this whole story with the, 109 elements in the periodic table, that's much more complicated, right? And then you get to quantum mechanics, and you may think, well, now things get simpler again. And that's right, up to the point where you notice, well, there's this thing that's called the weak interaction. And then there's quantum chromodynamics. And quantum chromodynamics spits out all of these mesons and bosons and so on and so forth. And it makes things more complicated again. It's never been just a path to simplification. It's always been ups and downs.
Yeah.
And so I'm like, well, maybe the next step is an up and not a down. Okay, so that's the simplification. And then there is this naturalness criterion. So naturalness is basically the opposite of fine-tuning. So these two words, they belong together. A theory is natural if it is not fine-tuned. So people use this basically as synonyms. But in particle physics in particular, they're using a very specific notion of naturalness that's called technical naturalness, which is a little bit different. But the idea is basically that a theory should not have improbable coincidences. In principle, that's a good idea, and there are certainly examples where this is a good criterion. But the problem is that in the situations where physicists apply this criterion in the foundations of physics, there is no way to ever arrive at a proper probability distribution. They just assume it. So they're creating the problem by assumption. And I'm saying, well, that's not, you can't conclude anything from that. You've created the problem by putting it in. And indeed, it's easy to remove these problems just by putting in a different probability distribution. So the point that I'm trying to drive home there is that these are not actually problems with the theory. It's just that you don't like the theory for one reason or the other. And again, philosophers would say, well, that's a metaphysical criterion. Okay, so you can say, well, for some reason, I don't like theories which have this property. Therefore, I don't want to work with them. And yeah, you can do that. But the problem is that physicists in these areas, that they don't really realize that this is what they're doing. So this is why the book's called Lost in Math, because they put these requirements into the mathematics, and then they forget that they were just metaphysical assumptions.
Yeah, so they like something and they decide to go along with that thing they like, which is all these concepts that are not found anywhere in science. They're just coming from experience because maybe it worked sometimes, and they decide, okay, we want to go along with these concepts of beauty, simplicity, and naturalness because it worked maybe for Einstein and other similar scientists. So they think it will work in the future as well. Is that correct?
No, it's not. That's the irony about it. If you look at the history, you will find that actually arguments from beauty didn't work. It's just that the only cases that physicists seem to remember are the cases where it just, I would say, coincidentally did work.
Okay.
Like, for example, and then you can ask how relevant was it actually practically in the development of the theory. But it's certainly the case that Einstein and Dirac and Weil and some others went on and on about how important it is to pay attention to beauty and so on. But there were also a lot of physicists who went on about the beauty of the theories, and those theories turned out to be wrong. So it's like you're not looking at the control group if you're trying to make that kind of argument.
It's cherry picking.
Yeah, it's cherry picking. Exactly.
Yeah.
And it's the same with these arguments from naturalness. Arguments from naturalness have failed over and over again. Like they used naturalness to predict this particle called the axion, and that was falsified in the 1970s. Now, I should add here that they are still talking about a particle called the axion now. This is not the same axion. This is what was originally called the invisible axiom. Okay, so it's a variation of the original axion that was invented to avoid the constraints from the experiments at the time. And, the cosmological constant is not natural. It just isn't. And the Higgs mass, for all we know, is also not natural. So you have this series of failures, really, but still they cling on to this criterion, which is, I think it's just bad science. If you notice that your methods aren't working, you're supposed to revise them, and it's not happening.
Thank you for listening to this conversation with Dr. Sabine Hossenfelder. If you enjoyed it, please leave a comment below, like, subscribe, and turn on the notification bell. And please support this channel on Patreon. And thanks for watching.